Hello friends, my name is Manish Tiwari and today we are going to discuss about chemical kinetics. So the topics you can see what we are going to cover in this lecture is concentration versus time graph we are going to understand, and then order of reaction along with molecularity of reaction, and then we'll proceed to generalization of rate law and finally integrated rate law. So these topics we are going to see today. Okay, so first of all, before touching to the chemical kinetics, I am going to move your concentration to thermodynamics. Why? Because see, chemical kinetics definition is that it is the study of rate of the reaction. How fast is the reaction going? How slow is it going? Okay, so that we discuss in chemical kinetics. But uh, when we ask the same thing with thermodynamics, so thermodynamics tells us about the uh, entropy of the reaction, the enthalpy of the reaction, okay, gives free energy, okay, work done, first law from first law of internal energy, okay. So all this thermodynamics tells us, but it doesn't touch upon the rate, how fast it is going to be, okay. It will tell that okay, this reaction will be spontaneous, because we know that if delta G is less than 0, the reaction will be spontaneous, okay. Or if delta S total is greater than 0, then the reaction will be spontaneous, okay. So what we are going to ask with chemical kinetics is basically the rate of reaction with respect to time. So how it proceeds with respect to time, how concentration is changing, how pressure is changing, okay. So let's first talk about concentration versus time, okay. So the first thing is we are going to take a hypothetical equation A to B, right. In A to B we have a reactant A and product B. So we have taken its initial concentration as A0 and B as 0, okay. So now with time A is going to disappear, okay. A is going to disappear and in the same extent B will form, right. So we have decomposition of A and formation of B, right, means disappearance of A and appearance of B, okay. So the graph which comes out is looks like concentration versus time. A is going to be look like this concentration of A, and the concentration of B, it is increasing and then it is going to be constant. And in the case of A, so this is our concentration A0, okay, the initial concentration of A. So the initial concentration of B was 0, right. So A is going to disappear, its concentration is going down, and then it is going to be constant, right. And in the case of product B, its concentration is increasing and then finally it will be a constant, okay. So here one thing we ask about, that how the rate of the reaction is in this equation, okay, in this chemical reaction. So rate of reaction we study in two different ways. First, average rate of reaction, and second, instantaneous rate of reaction, okay, instantaneous rate. So first let's talk about average rate of reaction. Okay. So in a time interval from, let's say, T1 to T2. Okay. So this is our A1 and this is concentration A2, and this is B1 and this is B2. Okay. So in time interval from T1 to T2, the change in concentration what we are observing is from A1 to A2, right? So what we can write is that average rate of reaction will be equals to A2 minus A1, the final concentration, A2 minus A1, put it inside, divided by T2 minus T1. Okay, and one thing we have to notice that A2 is less than A1. Okay, A2 is less than A1. So that is why this average rate, this rate will be for disappearance. This will be negative. A2 is less than A1. Okay, so the overall rate will be negative because T1, T2 cannot be negative where the time is increasing. Okay, time is positive. T2 is greater than T1. T2 is greater than T1. Okay, so this is our average rate of reaction. But in case of concentration of B, you will have average rate will be B2 minus B1 upon T2 minus T1. Okay, this will be positive because B1 to B2 it is increasing. Okay, so B2 is greater than B1, so that is why the average rate will be positive. Okay, so this we have seen average rate of reaction. Now come to instantaneous rate. So what do we mean by instantaneous rate? So at any point of time, at any instant, the rate of the reaction will be called instantaneous reaction. For example, at time t, let's say at time t, we have concentration A and concentration B. Okay, in the reaction we have these concentration of reactant and product. So what we can write is that the rate now will be written in terms of differential, right? Minus dA by dt. This is instantaneous rate for A. And why negative? Because A is decreasing. Okay, and in case of B, it will be positive dV by dt. Okay, so the rate will be same. The rate of disappearance of A and the rate of appearance of B will be same. Okay, so this is our concentration versus time. Now let's move to order of reaction. Okay, so order of reaction is basically experimental quantity what we are going to measure. Okay, it is order of reaction, it is experimental and it can be 0, 1, minus half, plus half, okay, fractional and all that. So basically order we determine with respect to a particular reactant, right? For example, let's take this reaction A plus B going to be forming the product C. So for this, if we write the rate law, it will be rate R is equals to rate constant K into concentration of B to the power A and concentration of B to the power B. So the rate of the order of the reaction, with respect to concentration A, reactant A is A, small a, and with respect to B will be small b. So the overall rate will be A, order will be A plus B. Overall order will be A plus B. Okay. So this is our order of reaction, and let's also cover first the molecularity of the reaction, and then we'll move to the generalization of rate law. Okay. So molecularity of reaction basically, so it is defined as number of effective atoms or molecules colliding to form the transition state, right? So they are going to lead to be a product, right? So for a chemical equation, how we determine the molecularity is that, let's say 2,8 it is forming B, so the two atoms of A or molecules of A is forming this transition state. Now it is going to be form B. Okay. So the molecularity of this particular reaction will be 2. Molecularity will be 2. That means it is a bimolecular reaction. It is a bimolecular. Similarly, A plus B plus C forming D. Okay, so the transition state can be A, B, C, right? So now it will be a trimolecular reaction. Molecularity will be 3. So molecularity, you can see, it can never be negative, it can never be 0, and it can also never be in fraction. Okay, so this is our molecularity of reaction. So it is also a theoretical concept, right? And if you we have observed that molecularity are never observed more than 3, because there won't be any effective collision if we take 4 molecules all together, right, colliding each other. So there won't be effective collision. So that is why more than 3 molecularity is not observed. Okay. So let's move to the generalization of rate law. So let's take first a chemical reaction A plus D, right? And let's take the initial concentration of A as A0 and B as B0, and for C and D 0, right? At T is equals to 0. At T is equals to T, it will be A0 minus AX, okay? And B0 minus BX. It will form CX and DX. Okay. Now let's write the rate of reaction with respect to A. Okay, so minus dA by dt, it is equals to minus d. At time t, we have the concentration A naught minus AX. A naught minus AX. Okay, now it will be minus dA naught by dt minus plus, and it will be A is constant, it will come out, it will be dx by dt. Right? A is constant and x is variable, so it will be A dx by dt. So minus dA naught by dt, it will be 0 because it is constant and differential of derivative of constant is 0. So now we have minus dA by dt is equals to plus A dx by dt, right? So dx by dt will be minus 1 by A dA by dt, minus 1 by A dA by dt. Similarly, in the same format, for B, it will be dx by dt is equals to minus of 1 by B dB by dt. Okay, so we just have to put replace just A to B. Okay, that is we have to do only. A to B, B, and this small a will be small b, B, right? B. So we will now have dx by dt is equals to minus 1 by b dB by dt. Okay, minus we have taken in both the cases because it is disappearing, right? We have seen in the instantaneous rate of the reaction during. So next we have rate of appearance of C and D. So it will be plus dC by dt is equals to C at time t is equals to t, it is Cx. So we'll just put it Cx, C will come out because it is constant, dx by dt. So dx by dt will be equals to dx by dt will be equals to 1 by C dC by dt, right? Okay, so now we'll equate all this dx by dt term. Okay, so we'll get a general equation that will be called general rate law equation. So that is minus d 1 upon A dA by dt is equals to minus 1 upon B dB by dt is equals to plus 1 by C dC by dt is equal to plus 1 upon D by dt, right? So this is our general rate law equation. Okay, yeah. So let's move to the integrated rate law equation.